And the last speaker for the contributed sessions, Alejandro is going to speak to us about weighted conformal invariance of Banach spaces of analytic functions. Thank you so much.
Thanks. First of all, I want to thank the organizers to let me the opportunity to do this talk. This presentation is based on a joint work with Professor Alejandro of University. We begin with some notation and background that will be useful for us around this talk. For example, we will denote in the usual way the unit disk and the unit circle, and we denote in this way the space of all holomorphic functions in the unit disk and the group of automorphisms of the unit disk. Now, I will present or recall some classical spaces of analytic functions in the unit disk that we will use later. For example, we can start with the classical Hardy spaces. If we consider an analytic function f in the unit disk, then its integral means are given by these formulas. The first formula when p is finite, and the second formula when p is equal to infinite. So we will say that an analytic function f is in the Hardy space Hp if the supremum of this integral means is finite. Some properties of these spaces. For example, if we consider a function f in the Hardy space Hp, then its radial limits exist almost everywhere. Moreover, when p is finite, the polynomials are dense in the Hardy space Hp, and we have the following pointwise estimates. On the other hand, when p is equal to 2, the Hardy space H2 becomes a Hilbert space with this scalar product. Other important spaces of analytic functions in the unit disk are the weighted Berman spaces. The weighted Berman space, AP beta, consists of all analytic functions in the unit disk, such that this integral with respect to the area measure is finite. Some properties of these spaces. The polynomials are dense in the weighted Berman space AP beta, and we have the following pointwise estimates. As in the Hardy spaces, when p is equal to 2, the weighted Berman space A2 beta becomes a Hilbert space with this scalar product. So now the last spaces that I want to present in this part will be the weighted Bezoff spaces. The weighted Bezoff space BP beta consists of all analytic functions in the unit disk whose derivative belongs to this weighted Berman space AP beta. We can equip this space with this norm, or also, for example, with this equivalent norm. These spaces, these weighted Bezoff spaces, are also called weighted Dirichlet spaces, but we only use this terminology or this name for the Hilbert case. I mean, when p is equal to 2, as in the previous spaces, B2 beta becomes a Hilbert space with this scalar product. So in this case, we will call B2 beta a weighted Dirichlet space, and we will denote it by D2 beta. So in this presentation, we focus on a concrete weighted conformal invariance property. First of all, I will recall the classical concept of conformal invariance. If we consider a reasonable Banach space of analytic functions in the unit disk endowed with a seminorm ρ, then we will say that our space is conformal invariant if for any function f in our space, f composed with any automorphism phi remains in our space. And moreover, there exists a positive constant such that we can control the seminorm of this composition with the seminorm of f, uniformly for any automorphism phi. Some examples of classical spaces of analytic functions in the unit disk that satisfy this property, for example, the block space that consists of all analytic functions in the unit disk such that the supremum is finite. This block space is conformal invariant. And moreover, this space plays a crucial role in the study of this classical conformal invariance property. I will talk about it later. More examples. The classical Dirichlet space is also conformal invariant, and the space BMOA that consists of all analytic functions in the unit disk such that the supremum is finite is also conformally invariant. So in this talk, we will study the invariance under this weighted composition operator, W alpha phi. If we see in the classical conformal invariance property, it studies the invariance under the composition operator whose symbol is an automorphism. So here, instead of considering these composition operators, we will consider these weighted composition operators, where phi is also an automorphism. To be precise, we will say that a Banach space of analytic functions in the unit disk is conformally invariant of index alpha if our space satisfies the following properties. Property 1, our space is continuously contained in the space of holomorphic functions in the unit disk. By the uniform bondedness principle, this is equivalent to say that the point evaluations are bounded in our space. Property 2, for any function f which is analytic in a disk of radius greater than 1, then this function is in our space. And the last property, property 3, there exist two positive constants, alpha and k, such that we can control the norm of these weighted composition operators uniformly for any automorphism phi. With these three properties, we can deduce, for example, that this constant alpha is unique. Is unique in the following sense. If we consider a conformal invariant space of index alpha, then this space cannot be conformal invariant of other index beta. Some examples of classical spaces of analytic functions in the unit disk that satisfy all these properties. For example, we can start with the Hardy spaces. When P is finite, the Hardy space HP is conformally invariant of index 1 over P. More examples. The weighted Berman space AP beta is conformally invariant of index 2 plus beta over P. And also, we can consider the Korenblum spaces. These spaces are also called growth classes, and the Korenblum space A minus gamma that consists of all analytic functions in the unit disk such that the supremum is finite is conformally invariant of index gamma. Even we can see that in all these examples, in all of these three types of examples, the weighted composition operator W alpha phi defined in property 3 is actually an isometry. On the other hand, if we consider this space a log that consists of all analytic functions in the unit disk such that the supremum is finite, we can see that this space satisfies property 1, property 2, but fails to satisfy property 3 for any index alpha greater than 0. The same happens with the classical drilled space. However, if we impose certain restriction about the parameters, we can see that the weighted best of space BP beta is conformally invariant of index 2 plus beta over P minus 1. Now, we begin with the study of our weighted conformal invariance property. First of all, we will see the relation between our invariance with some standard objects. In this part, we will consider two Banach spaces of analytic functions in the unit disk, x and y, satisfying property 1, or the point evaluations are bounded. With this hypothesis, we can define this space of pointwise multipliers from x to y as the space of all analytic functions in the unit disk U, such that U times any function of x belongs to the space y. And we can equip this space, for example, with this norm. On the other hand, we can define the weak product of x and y as the space of all analytic functions in the unit disk with the representation such that this infinite sum is finite. So what is the relation between our invariance and these spaces? If we consider a conformal invariant space of index alpha, x, and a conformal invariant space of index beta, y, then if alpha is greater than beta, this space of pointwise multipliers from x to y is trivial. On the other hand, if alpha is less than beta, then this space of pointwise multipliers satisfies property 3 with index beta minus alpha. What is the problem here? We don't know if this space of pointwise multipliers satisfies property 2. For example, if x is not included in y, then the constant function 1 does not belong to this space of pointwise multipliers. So if we add this extra hypothesis that this space of pointwise multipliers satisfies property 2, then this space will be conformal invariant of index beta minus alpha. Finally, the weak product of x and y is conformal invariant of index alpha plus beta. Now, we pass to study the relation between our invariance with some one-parameter abelian operator groups. We know that the group of automorphisms of the unit disk contain several one-parameter subgroups. For example, these two ones. These subgroups induce these other operator groups. So here, the question is the following. If we start with a good space, by good, I mean a conformal invariant space of index this alpha, can we expect some good properties of these operator groups? For example, are these operator groups extremely continuous? The answer is no. In general, no. We have to add some extra hypotheses. This hypothesis is the density of the polynomials. With this, we can prove the following. If we consider a conformal invariant space of index alpha such that the polynomials are dense in our space, then the uniform convergence on compact subset of the unit disk of this sequence of automorphisms phi n implies the strong convergence of these operators, of these weighted composition operators, W alpha phi n. The polynomial approximation is a basic topic regarding Banach spaces of analytic functions in the unit disk, and usually is closely related with the semigroup of dilations. We will also see the relation between this concept with this group of rotations. In this part, we will relax our property 3. Instead of considering all these weighted composition operators W alpha phi, we will only consider in our property 3 prime these rotation operators. With this, we can prove the following. If we consider a Banach space of analytic functions in the unit disk satisfying property 1, recall the point evaluations are bounded, property 2, for any function f which is analytic in a disk of radius greater than 1, this function is in our space, and this weak property 3 prime, then the polynomials are dense in our space if and only if this group of rotation is strongly continuous in this interval, and this happens if and only if this semigroup of dilations is strongly continuous at 1. Using the same techniques that we used to prove the result, we can get the following sufficient condition. If our space satisfies property 1, 2, this weak property 3 prime, and we suppose that the linear span of point evaluations is dense in the dual space, then the polynomials are dense in our space. A good question here is the following. Is the converse of the result true? The answer is no. And we can find a counterexample with the classical Berman space, A1. Because we know that we can identify the dual of this Berman space A1 with the block space. And with this, we can get a contradiction. Using the previous result, we can get the following corollary. If we assume that our space satisfies property 1, 2, and this weak property 3 prime, and moreover, our space is reflexive, then the polynomials are dense in our space. Since we have talked about the dual space, what can we say about duality? In this part, we will consider a conformal invariant space of index alpha such that polynomials are dense in our space. we consider this assumption in order to identify the dual space with a space of holomorphic functions in the unit disk. So the question here is the following. Can we find a representation of this dual space that preserves our weighted conformal invariance property? The answer is yes. And in order to get the representation, we need to use these Hilbert spaces H alpha, whose reproducing kernel is given by this formula. The reproducing kernel induces this scalar product. But which are these spaces H alpha? When alpha is equal to 1/2, we recover the classical Hardy space H2. When alpha is greater than 1/2, we get these weighted Berman spaces. And when alpha is less than 1/2, we recover these weighted Dirichlet spaces. With these spaces in mind, we can define the following map U. U maps the dual space X prime into the space of holomorphic functions in the unit disk. In this way, we can see here the reproducing kernel of the space H alpha. Moreover, we will denote by X prime alpha the range of this map. So with this hypothesis, recall, our space is conformal invariant of index alpha, and we assume that the polynomials are dense in our space. Then, if we equip this space X prime alpha with this norm, we can prove that this space X prime alpha becomes a Banach space of analytic functions in the unit disk, which is conformal invariant of index alpha. And moreover, we can represent any element of our dual space in this way. So now, in the last part of this talk, we will pass to other different things. In 1979, Rubel and Timony proved that the largest conformal invariant space in the classical sense of conformal invariance is the block space. And 6 years later, Arachi, Fisher, and Petre proved that the smallest one is the base of space B1. The base of space B1 consists of all analytic functions in the unit disk whose second derivative belongs to this Berman space A1. And moreover, we can see the base of space B1 as the space of all infinite sums of disk automorphism with L1 coefficients. So here, the question is the following. Which is the smallest and largest conformal invariant space of index alpha? We will start with the smallest one. A good candidate for this space is this space X min alpha that consists of all analytic functions in the unit disk with the representation with L1 coefficients. We can prove that this space X min alpha satisfies property 1 and property 3. And moreover, this space X min alpha is continuously contained in any conformal invariant space of index alpha. What is the problem here? Does this space satisfy property 2? We can see more of this, because thanks to the atomic decomposition theorems, due to Kochman and Reuber for the weighted Berman spaces, and due to Peloso for the weighted base of spaces, we can see that this space X min alpha is actually this weighted base of space when alpha is less than or equal to 1, and is this weighted Berman space when alpha is greater than 1. So in particular, our space X min alpha is conformal invariant of index alpha. On the other hand, if we consider an arbitrary conformal invariant space of index alpha, then our space is continuously contained in the Korebloom space A minus alpha. We can see this claim with these few computations where we only use that our space satisfies property 1 and property 3. So with this, we can say that the largest conformal invariant space of index alpha is the Korebloom space A minus alpha, and the smallest one is either a weighted base of space or a weighted Berman space. Following these ideas, in 1985, Arachi and Fisher proved that the unique conformal invariant Hilbert space, also in the classical sense of conformal invariance, is the drilled space, of course, up to equivalence of norms. So, is there a version of the result in our context? The answer is yes. We can see that the unique conformal invariant space, Hilbert space of index alpha, is this H alpha space. Recall that this space H alpha is either the Hardy space H2 or a weighted Berman space or a weighted Dirichlet space. Of course, all of this up to equivalence of norms. Some ideas of the proof of the result: if we consider a conformal invariant Hilbert space of index alpha, then in particular, our space is reflexive. So by the previous results, the polynomials are dense in our space. We can even see that this group of rotations is strongly continuous. So with all this information, we will define this equivalent norm in our space that induce this scalar product. Why do we consider this scalar product? Because the monomials are orthogonal in this scalar product. So we can represent this equivalent norm in this way, in terms of the Taylor coefficients. So now the strategy is try to compare this equivalent norm with the norm of the space H alpha, which is given by this formula. So to do this is enough if we can prove that these two inequalities holds for every n greater than or equal to 0. But we can even reduce this using the duality theorem, because if we can prove that this second inequality holds for any conformal invariant space of index alpha, then in particular, this inequality holds for the space X prime alpha. And with this information, we can deduce that the first inequality also holds. So now, to prove the second inequality, we will use an argument based on asymptotic estimates of this norm. Here we can see the weighted composition operator that appears in property 3. So this is all I want to say. Thanks for your attention.
Thank you very much. Does anybody have any questions for the speaker?
Hi, Alejandro.
I just wanted to say I enjoyed your talk.
All right, if nobody has any questions, let's thank the speaker again. And this terminates.
Oh, sorry, please.
No, I was just going to say this terminates the contributed sessions for the entire field's semester. So I think the only organizer here is Javad. I'm not sure if he's there, but maybe let's thank Javad.
I hear you.
So thank you so much, Javad, for planning this, and I look forward to the last few days of the very long and very complete field semester.
Thank you indeed. I mean, and thank you to all participants. It was something really special. I mean, I've never been so involved in my academic life for more than 25 years. But frankly, I'm happy because I myself got a lot out of this focus program. I mean, it is useful for everybody around, I'm sure, but for myself too. And I mean, 16 weeks of conferences kind of consecutive is something.
That was great work, Javad.
Thank you. Thank you, Alexander.